molecules is looking at the atom that's like the central atom. So it's always the atom like in the middle. Okay, so we're just looking at the central atom in each case. That's always A. So even if it's a carbon, they call it A. If it's a nitrogen, they call it A. If it's an oxygen, they still call it A. So A just kind of represents the central atom. So B, the number you put with the B is the number of groups connected to the central atom. So it might be one single bond. You might have 2 single bonds, 3 single bonds. Every single bond counts as a bonded group. Every double bond counts as one bonded group. So if I have a double bond from a carbon to an oxygen, that counts as one bonded group. Even if I have a triple bond, that counts the same. Because remember that those are pairs of electrons that are kind of stuck between the two atoms. So they're considered like one group. So single, double, and triple bonds count as one group. The N is the number of non-bonding electron pairs that's around that central atom. Carbon, which looks like this, right? Remember that carbon will never have non-bonding pairs. Carbon, all 4 of its electrons are involved in covalent bonding, whether they're 4 single bonds, 2 double bonds, a double bond, and 2 single bonds, whatever. Carbon will never have an N associated with it. So if I have CH4, what would the ABN be for the carbon with CH4? If carbon's the central atom, how many groups connected? 4. So it's AB4. So it's carbon with 4 single bonds is always AB4. Okay. What if I have a carbon with a double bond to an oxygen and 2 hydrogens? What would that one be? How many groups connected? 3. So that's B. B is how many groups are covalently bonded. Okay, and so then also, what if I have carbon like this? What would that one be? AB2. So the center atom is the A, like they just chose A to start off the thing. So they're all A something, AB4, AB3, AB2, but notice that carbon never has an N. But then look at NH3. So this one, if I have nitrogen, has to be my A, right? Because it's the one in the middle. How many groups are connected to the nitrogen? 3, so this would be AB3. But how many non-bonding pairs belong to the nitrogen? 1. So this would be AB3-1. Or sorry, AB3N. You don't have to put a 1 with it if there's only 1. So nitrogen always has an N, because nitrogen will always have those non-bonding pairs. Oxygen will always have that. Oxygen is always going to form 2 bonds. Now, if it forms a double bond, it's not really going to make a shape. It's not going to have a central atom because it's just going to be two things just linked together. But if oxygen has 2 single bonds, now it's AB what? 2, because it's got 2 hydrogens connected. But how many non-bonding pairs does it have? Yeah, so that one would be an N2. So the N is just how many pairs of electrons belong to the atom. Oxygen will always have 2 N's. Nitrogen will always have 1 N. Carbon will never have any N's. So you can see in this one, and in fact, this shows this is the AB4. AB4 if you have carbon with 4 single bonds. And it doesn't matter. Like I could change these hydrogens and I could put in chlorines. So I could have chlorine, 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 chlorine. All those chlorines would have dots. Remember, they all have non-bonding pairs. Those dots are not around the carbon, so they don't matter. It's only the non-bonding pairs on the carbon or on the central atom that you count. That is always going to be this shape. They call that a tetrahedral. Remember, tetra means 4. So tetrahedral is sort of like a 4-pointed pyramid. The second one, though, shows NH3. So I could have, just like this image shows, that image shows, I could have NH3, But again, I could do something like this. It doesn't have to be hydrogen on it. Any nitrogen with 3 single bonds is going to form this, the AB3N, because remember, these non-bonding electrons take up room and they push the bonding electrons away. So they create this like repulsion. And so that is going to form the AB3N, characteristic of nitrogen, and that's always a pyramidal shape. Nitrogen with 3 single bonds would form a pyramidal. Carbon with 4 single bonds will always be tetrahedral. The next one's oxygen. So when you look at oxygen, the oxygen, and again, I could like put bromines on here. It doesn't have to be hydrogens. The key thing is I'm not looking at the bromines and their non-bonding electrons, I'm looking at the oxygen. So when I look at the oxygen, I see that that oxygen has 2 non-bonding electrons and 2 groups attached. So the 2 groups attached is the AB2, and the 2 pairs of non-bonding electrons is an N2. And remember that these non-bonding electrons, they push the bonding pairs away, and that's the reason that you always end up, the single bond oxygens always end up with a bent appearance. They don't get straight across from each other. They end up having this sort of bent angle. So you can put in a little note, oxygen with 2 single bonds will always look bent. Kind of an easy way to pick it out. Nitrogen with 3 single bonds is always going to look pyramidal. Carbon with 4 single bonds is always going to look tetrahedral. So these last 2, these you really see if the central atom is carbon, because notice there's no non-bonding electrons, and the central atom has at least 1 double bond. So if you have a carbon with a double bond and 2 single bonds, then notice how this is equal. The distance, the angles of the oxygen to hydrogen, sort of their spacing. Do you see how it ends up being very equal, unlike the pyramidal that NH3 does, where you got those non-bonding electrons. If there's no non-bonding electrons, bonding pairs get as far apart as possible. So in fact, these would all end up being, like 120 degrees, 120 degrees, 120 degrees. Like they'd all have the same bond angle, okay? A third of a circle. So 360 is a circle. So each one would be a third of a circle apart. So you get this evenly spread angle. That is why it looks flat and it looks like a triangle. So that's where this name comes from. So trigonal means triangle. Planar means flat. And this will be a carbon with 1 double bond and 2 single bonds. And that's the AB3. Then the last one. So the last one's an AB2. So AB2 means that I have a carbon with 2 single bonds. If they have a carbon with 2 bonded groups, those groups will get as far apart from each other as possible, so they get on opposite sides. And in that case, you end up with something that looks like it's 180 degrees on both sides, right? So this is as far as negative electrons can get from each other compared to like having them close together. So that is linear. So this is a carbon with 2 bonded groups. So if there's no N in the numbering, you know it's a carbon, right? If there's 1 N, then you know it's a nitrogen. If there's 2 N's, you know it's an oxygen for us. There may be more, but for us, these are the only 5 you have to worry about. Okay, so in this one, so just a couple of them, you tell me. So what's the ABN for this one? A, B, 3. Remember, that would be trigonal pyramidal, or planar, sorry. Okay, what about the next one? This would be AB, AB2. See how the carbon has 2 groups connected, okay? So it doesn't have to be a carbon with 2 double bonds. It could be a carbon with a double bond, a single bond and a triple bond. And this one is going to be what shape? Linear, because remember, I always think it looks like a straight line, so linear. Okay, what about this phosphorus? So pH 3. This would be A, B3, N, right? Because it's, remember, N is per pair. So if you have 2 electrons, that's a 1 N. 4 electrons would be 2 Ns. And this one is the pyramidal. And then here's the last one. So what would this AB go? AB2, N2, good, right? So that sulfur has 2 groups connected and 2 pairs of non-bonding electrons. The B is how many groups are connected. The N are the non-bonding groups, and this would look bent. So the important thing in terms of the shape part is so that you can actually look at a covalent molecule and, one, see the shape. So if you look at this molecule, so this is ethanol. So this is CH3CH2OH. So ethanol, or wood alcohol. If you look at all the atoms that are kind of in the center, you can never talk about the geometry of a hydrogen because hydrogens just connect to one thing. So there really is no 3-dimensional shape. But if you have more than one thing bonded to you, then you can end up having a shape. So notice 2 carbons both have shape in this, and the oxygen on the end, because they have more than one thing. So if I look at this carbon, the question is, well, how many groups are connected? So this has 4, right? So that's why this is an AB4 and it's a tetrahedral. Carbon with 4 single bonds is always a tetrahedral. But then if I look at the middle carbon, what do you think here? How many groups are connected to it? 4. And they don't have to be the same things, right? It's just 4 single bonds. So it's also an AB4 and a tetrahedral. Then that oxygen that's down on the end. So if we look at the groups, how many groups does it have bonded to it? 2, so that's AB2. And then how many non-bonding pairs does it have? 2. And that's why it's bent. So this kind of leads into the next chapter where we're going to look at some bigger molecules and the fact of their shapes really do come into play. We can also apply this to what's known as polarity. Okay? So covalent molecules have this characteristic that ionic molecules do not. Covalent molecules can share their covalent bonds equally or unequally. And it really comes down to these 4. So if you look on your periodic table, do you see nitrogen, oxygen, fluorine, chlorine? Notice that these ones are all in the upper right-hand corner. These are very small atoms. And they have an almost full set of electrons. So that means they hold their electrons really tight. So if I was just going to draw, like if I was going to draw a hydrogen, I just put its electron here. But if I was going to draw a fluorine, I would actually think of the electrons as being really close to the fluorine, kind of like pulled in really tight. And it's because fluorine has 7 valence electrons. 8 valence electrons makes it stable. And that is why it pulls or holds its electrons tighter. So because it only needs 1 electron, it holds its electron tighter and it's not going to share with other atoms unless they're also electronegative. So here's an example. So on this, and if you look at the periodic table, remember that covalent molecules are only the yellow. So I don't know why they put I guess they put the purple and the green in there to show you the difference. You don't have to memorize the numbers. We are not going to calculate them that way, but the numbers that you see below each of the elements is what they call the electronegativity. It is a number between 0 and 4. 0 means very low electronegativity. 4 is the highest possible. The higher the number, the stronger the attraction an atom has for its electrons. So the tighter in it pulls. So notice the one that is the most electronegative atom is what? Fluorine, the one with the highest number. So see that it is at 4. And the reason that it is the most electronegative is because it's like it's really small. So if you look, it's got 9 electrons. 10 makes it like neon. It's really small, and its electrons are really close to the nucleus, which means that they have a stronger attraction for the protons that are in the nucleus. The bigger the atom, the smaller the electronegativity. The less valence electrons, the lower the electronegativity. So notice that it increases as you go left to right, and it increases as you go bottom to top, which is why fluorine is the most electronegative. But nitrogen, oxygen, fluorine, and chlorine, they are all 3 and higher. So see, nitrogen's a 3.0, oxygen's 3.5, fluorine is 4, chlorine is 3.0. None of the other ones are higher than them. So those are the ones that I say are really the big 4. And those are the ones you always look for. So say for example, if I have 2 hydrogens, remember that they make a covalent bond. They share their electrons, so up in the top. But they're going to share them equally because they have the same attraction for their electrons in the sharing. So I can think of those dots as being like right in the middle, like a 50-50. 50% of the time the electrons are over here, 50% of the time they're over here. So they're equally shared. Even oxygen, which is an electronegative atom, if you have O2, they both have the same attraction. So I tried to draw their little electrons closer to the non-bonding ones or closer, but they still have to share those equally because they have the same attraction. If they have the same attraction, if there's no nitrogen, oxygen, fluorine, or chlorine in a molecule like H2, then you know that the bonds are shared equally, and that molecule is said to be nonpolar. So a molecule like CH4. So we've drawn CH4 over and over and over again, the tetrahedral. It was the first molecule that you built in lab. So CH4 doesn't have a nitrogen, oxygen, fluorine, or chlorine, so you know that it's nonpolar. It shares the covalent bonds equally. Okay, so if it's nonpolar, it shares the electrons equally. If there is more than one nitrogen, oxygen, fluorine, or chlorine, then you have to look at where they are. Like I said for O2, because there's 2 of them, they both have the same attraction, but they end up having to then share the electrons equally. If there's more than one, you want to look at the shape. So it's really the big reason why we talked about shape in the last section, is because in shape, when you look at the shape of like CO2, my example down here on the right, carbon dioxide has 2 oxygens, but they're on opposite sides of each other and they balance the electronegativity. So CCO2, kind of like how O2 is. So O2, the 2 oxygens have to share their electrons because they both want to pull at the same sort of strength. Same thing with CO2. So because you remember that it's linear, that helps you to remember that it is going to be balanced in the electronegative numbers and it's nonpolar. But rule of thumb, down the center, okay? So this rule of thumb is if you have a molecule with less than 8 atoms, so I would say that's small molecules with only one nitrogen, oxygen, fluorine, or chlorine never shares its electrons equally, and it's always polar. Okay, so looking at the molecule of water, H2O. So H2O is right here. So you see that you've got the oxygen and the two hydrogens. There's only one oxygen. You can say without a doubt it's polar. Because what's going to happen is that oxygen's going to pull the electrons closer to it. The electrons will spend less time around the hydrogens. That's going to create a slight negativeness. And what this does, and there's this one up at the top, HCl. So I have hydrogen and I have chlorine. The hydrogen is the one with the little purple electron dot. The chlorine's the green, and it's got it 7. So notice where I drew those electrons. I put those electrons really close to the chlorine, further away from the hydrogen. That means that this side becomes slightly negative. That's what that funny looking little 8 symbol, it's supposed to be a delta symbol, like a Greek delta symbol. So then this side becomes slightly positive because they do not share electrons. The side where the electrons are more end up being slightly negative, and that creates polarity. Mm-hmm. It's because of this, because of this number. Because chlorine has an electronegativity of 3.0, hydrogen only has 2.1. So when the difference between those tells me that the electrons get sucked over to the chlorine compared to the hydrogen, they do not share their bonds equally, and that's why it ends up being polar. Okay, yeah, and they showed this one. This is kind of like their example of it is if you look at, oh, I had it. If you look at this one, one more time. Okay, never mind. So if you look at the one that's down at the bottom, okay, so see hydrogen, H2, that's this. That's H2. So see how those red dots look like they're exactly between? You're still into it. I love technology, okay? But if I look at HCl next to it, do you see how the electrons that are shared are like pulled over to the chlorine? So that, remember that those dots are negatively charged. So now I've got more negative electrons around the chlorine compared to the hydrogen, and that is why they use, there's the symbol that they use. Mine always looks kind of like that. I'm not sure it's just really hard for me to draw that as a normal rule. So the side where the NOFCl, that's really all that you want to look for. If you want to know if something is polar, look for a nitrogen, oxygen, fluorine, or chlorine. If you only see one, then you say, yep, it's polar, and move on. Okay? Because it'll never share electrons evenly with other things. If there's more than one, then you need to know, well, where is it? Are they on opposite sides? Are they all around the molecule? But the NOF and Cl, those are always going to be the ones that become more negative. So if I had this, so you look at this, you're like, well, it's small. It's a small molecule, but does it have a nitrogen, oxygen, fluorine, or chlorine? Yeah, that's 4 of them. Are they balanced? Yes, this is nonpolar. And it's because they're balanced. But if I had this, is there a nitrogen, oxygen, fluorine, or chlorine? Yes. Are they balanced? No. If you can arrange and put them on one side of the molecule, then you know that side becomes negative, that side becomes positive. So you're really just looking for those 4. Nitrogen, oxygen, fluorine, or chlorine. If you only have one, you know it's polar. But if you have 2 or more, you want to know like how they're arranged. Okay? Because that's why I said if you have like CO2, you know those are on opposite sides of each other. But if I look at H2F2, You know that's a tetrahedral. So I could put the fluorines on one side. By flipping around the molecule, I could get the fluorines on one side, hydrogens on the other side, and that would definitely separate and create the polarity. So what's the plus of this, or what's the reason for understanding, is polar molecules end up with this uneven distribution. They end up with this slight positive and slight negative sidedness to the molecule. Whereas nonpolar, I would consider nonpolar is completely neutral. So something that's nonpolar is like a pen to a magnet. Doesn't do anything, okay? Plastic, neutral. Doesn't have any kind of charged nature. But we've talked about covalent and ionic. Which is ionic more like? A polar molecule or a nonpolar? Because polar has slight positive and negative. Ionic is positive and negative ions. And so now we can actually put them together and talk about things that are polar, things that are nonpolar, as sort of a general understanding. So remember that these have a slight charge. Water, best example, really polar molecule. So that means that if I have other liquids that are also polar, I can mix them into water and they mix and stay mixed. And so ammonia, NH3. That can be mixed with water. You can dilute ammonia. It completely mixes, doesn't separate, because both water and ammonia are both polar. Vinegar, same thing. So like I had to clean our coffee pot out with the vinegar solution this weekend. But you can put vinegar in, run it through the pot, then you just keep rinsing with water, and the vinegar dilutes in the water, so it mixes completely. Vinegar, also a polar molecule. You can even take solids, like table sugar, and add it to a polar liquid, and they'll mix and stay mixed. So in theory, you could take sugar and put it in vinegar and shake it up, and it would dissolve. Okay? All of these can mix together because they all have this slight positive, negative chargedness. So they say polar things mix with things that are polar. The other thing, though, salts. So remember when we were talking about salts, and I said if you take NaCl, which is table salt, and you put it in water, it splits into sodium ions and chloride ions. They become aqueous. Aqueous means dissolved. They don't stay together as a solid. They're able to dissolve, and they even separate. In fact, that's how sodium is found in your blood. Your sodium is not found as sodium chloride as like together. They actually free float in the blood because of their ability to interact with polar water. Those charged ions are attracted to them. So polar mixes with polar. Polar can mix with ionic. Then you got the other category. The other category are things like Cl2, O2, CO2, CH4, all of those carbon molecules. If there's no nitrogen, oxygen, fluorine, or chlorine, then you're going to find that they're very uniformly shared. They form very neutral molecules. Neutral molecules don't have much attraction for other molecules. Like I say, it's like two pieces of plastic, okay? They tend not to stick together. They tend not to have this attraction. But there's a couple of types of categories that you can kind of think of whenever you think that are things that are nonpolar. Things that are nonpolar tend to be greasy, oily, waxy. So things like fuels, so like gasoline, kerosene, diesel fuel, they're all nonpolar. Grease, this can include like olive oil, vegetable oil, canola, all the cooking oils, as well as stuff like butter, lard, shortening like Crisco. all of those, you know, if you get them on your fingers, they're sort of slimy feeling, okay, greasy feeling. And what happens when you just run your hands underwater if you get it on you? Does it come off? No, because the oil like sticks to your fingers and does not want to mix with the water. So you have to do special things just to try and wash the greasy stuff off of your hands, your dishes, etc. So polar things, though, they'll mix with polar things. So you can take like butter, melt some butter in a pan, add some olive oil, mix it up, they'll mix. Okay? Things that are non-polar mix with things that are non-polar. So you could take gasoline and oil. In fact, that's what they put in like weed whackers, is you use like that 2-cycle engine oil. So you get like a gallon of gas and pour this small little container of oil because it burns both of them at the same time. So all of those things would mix. The big kicker, though, is that you cannot mix non-polar molecules with salts. You can't mix non-polar molecules with polar molecules. They'll just separate. So like the next time that you're going to fry something, put your bit of oil in the pan and put some salt, just shake some salt, and you'll see the salt just drops to the bottom. You can take like your little spoon and stir it. It won't dissolve. It stays a crystal because it doesn't want anything to do with the neutral oil molecules. There's no attraction to create that blending or that mixing that allows it to dissolve. Okay, so that's really kind of introduce this idea of polarity. So the last thing in chapter 3 is about counting. This is the only math on this test. And it was because molecules are so small, chemists were like, well, how do we count these? How do we measure them? What do these atomic masses have to do with anything? How can we measure out like 12 atoms or 10 atoms or even 1,000,000 atoms because it's such a small amount? So they came out with a counting unit that they call the mole. Okay, I don't know how MOL, unless it kind of was like short for molecule, maybe that's where the name came from. So this term mole is kind of like a dozen. Okay, that's sort of the rationale. You're like, well, where'd they come up with a dozen? I don't know, maybe it's what could fit in a bowl comfortably or something like that. Like, why did they come up with a 12? I don't know. Why did they just use 10? That would have been easier. You could have had 10, 20, 30. You wouldn't have to learn to count by 12. But that's the same thing here. So the mole equals two things. So the mole is equal to the formula mass of any molecule expressed in grams. Okay? So if I have 1 mole of carbon, you look at the periodic table, you find the atomic mass for carbon. The atomic mass for carbon is 12.0108. Just round it to a whole number. There would be 12 grams in 1 mole because the formula for carbon is just C. Just 1. So if I have 1 mole of water, and I want to know how many grams, do you see how it looks like a unit conversion? Right? Like how we did like 100 meters is how many millimeters? This is kind of like 1 mole of water is how many grams. But instead of using the metric conversion, you just use the formula mass. So you're going to look up the mass of 2 hydrogens and 1 oxygen and add them together. So I have 2 hydrogens. Each hydrogen weighs what? Look on your periodic table. 1. So that's going to add 2 grams. I have 1 oxygen. And each one weighs 16. I just add those up. So 16 plus 2 tells me that there is 18 grams in 1 mole. As long as you have a periodic table, you can figure out how many grams in 1 mole of anything. Okay, so figure this out. 1 mole of H2SO4, which is sulfuric acid, is equal to how many grams? Use your periodic table to solve for this. Always you get the mass. It's always the number with the decimal place. Round to a whole number. You don't have to keep the decimals. Just round them. It's always the bottom number. What you get as a number? What you get as a number? 98. Anybody not get that? Okay, it's just 2 hydrogens times 1, 2 grams. 1 sulfur times 1, or each one weighs 32. So that's 32 grams. And then 4 oxygen, each of them weighs 16, so that's 64 grams. So I just add them up. That's where I get 98. So 98 grams in 1 mole. So if you know 1 mole, then you can figure out 5 moles. You can figure out 10 moles. You can figure out 0.065 moles. You can figure out any amount. All you're going to do is find the formula mass. They call this the gram formula mass because it's just the mass of each of the atoms. You just put grams at the end. Okay? So the other thing, so I said the mole, 1 mole, is always equal to the gram formula mass. The mass of the molecule expressed in grams. But they also wanted to know, okay, well, how many particles is this? And this was something that Avogadro worked on pretty much his entire career, his entire lifetime. He was trying to calculate how many particles would be in 12 grams of carbon, okay, or 1 gram of hydrogen. And so he was trying to determine how far apart are molecules compared to their atomic mass. So how big are they? How far apart are they? And then how many particles would actually be in that mass amount. And he actually got really, really close, considering he did this like 400 years ago. So this was not something that he just happened anytime soon. It was quite a long time ago. So he also found out that 1 mole is equal to 6.02 times 10 to the 23rd molecules. Molecules, particles, atoms, if we were talking about atoms, like if we were talking about a mole of carbon atoms, 1 mole of carbon atoms would be 6.02 times 10 to the 23rd. 1 mole of water would be 1 mole of water molecules, because that's typically when you have a compound, you just refer to them as molecules, so that would be 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd is this. It's 602 and 21 more zeros after it. So that's a lot, because atoms are so very small. But it's much easier to talk about it in terms of exponents. And so in exponents, the challenge of exponents is making sure when you do exponents, you use exponents in math, that you actually don't mess up your numbers of exponents. So there is a button, and one of the reasons that I like these graphing or these basic calculators is everybody see the button above number 7. The button above number 7 is the EE button. That is your exponent shortcut. So if you put 6.02 6.02, and then press the EE button, do you see that two little zeros show up? Those are the exponents. So it automatically puts times 10 to the and puts parentheses around this number. So if you use this in a math calculation, it'll automatically have the parentheses. So now put 2, 3. So everybody has 6.02 EE and then 2, 3. They should look like they're smaller numbers. Yours looks like an E2, 3, like on a graphing calculator. Is that how yours looks like? So I put this in the calculator, 6.02, then I hit this EE button, and then I hit the 2, 3. And that's saying the same thing as 6.02 times 10 to the 23rd. So 1 mole of anything is 6.02 times 10 to the 23rd molecules. So I could substitute anything in there. I could say 1 mole of water would be 6.02 times 10 to the 23rd molecules. 1 mole of sulfuric acid, H2SO4, is 6.02 times 10 to the 23rd. So this is kind of like a unit conversion. So I can put, and that's his name. So Avogadro is the one that did all this measurements, and they actually named the number after him. So I can use this like a unit conversion. So I can have 6.02 times 10 to the 23rd molecules per mole, or I could have 1 mole over 6.02 times 10 to the 23rd molecules. The kicker is making sure you put it in the calculator right. So that's why we're just going to practice a couple of these. So here's the first one. So remember, we did this. So you know, so if I give you moles and grams, okay? So if you see moles and grams, if you see moles to grams or grams to moles in your problem, then you know you need to use the formula mass. Find the formula mass and set it up so your units cancel. Right, so the formula mass is going to be grams over moles or moles over grams. If you see moles in molecules or moles in atoms, then you use Avogadro's number. Pretty much stick to molecules, though. Then, I don't know what I did. So here, you'll have 6.02 times 10 to the 23rd molecules per mole. Right? Whereas you're using the formula mass, it's going to be numbers of grams per 1 mole or moles per gram. So this first one, the first one is 1.5 moles of H2SO4 is how many grams? So this is like a single unit conversion. I can do this in one step. I don't have to set it up multiple times or anything. I'm going to do this in one step because I'm just going to use the formula mass. And we actually calculated that back before. Remember, we found there was 98 grams per mole. So it really just depends on where you're starting. So if I have 1.5 moles of H2SO4 times in a line, and it's a single one. So what unit goes on the bottom? Moles, right? Because that's the one I want to cancel. So whatever unit you start with goes on the bottom, and your answer goes on top, which is grams. So 98 grams in 1. So do you see that moles and moles will cancel? It'll leave you with your answer in grams. So 1.5 times 98 ends up coming out as 147 grams. So now we got to go back to chapter 1 stuff, so significant figures. Our measured number is what? That 1.5. So the 98, you got figured out from the periodic table, right? To figure out 98 grams per mole, we use numbers off the periodic table. Those are not considered measured numbers. So it's always going to be your measured number. So it would be the 1.5. So in this, how many significant figures? 2. So that means the 1 and the 4, I keep. The next is a 7, so what would that do? Round it would round to what? 1, 5. So 147 would round to do I have to put a 0 at the end or no? Do you want to round $147 to 15? No. I would round it to 150. So remember the 0 at the end. If there's no decimal place, it's not significant, but you have to have it to show the size of the number. So then I can do the exact opposite, go the other direction. So if I have 50 grams of H2SO4, I can figure out how many moles. It's still just a single step. So you write down what you're given, 50 grams, and you don't even have to write H2SO4, but you can if you want. Times in a line, what unit goes on the bottom. Grams, the unit you're given always goes on the bottom. And that means the unit I want to get is moles. So there's still, again, notice in this one, 98 goes on the bottom, 1 goes on the top, because this is 98 grams per 1 mole. So 98 divided by, 50 divided by 98 gives me 0.510204082 moles. Can I keep all that? No, it's way too exact. How many significant figures in my problem? Just 1. Remember, because the 0 is not, only if there's a decimal. So that means, what am I going to round this to? 0.5, right? Because remember, the zeros out front are never significant. Zeros at the end are only significant if there's a decimal. So since there's no decimal in 50, then it's just one significant figure, so I would just round this to 0.5. Okay, so now let's try one with Avogadro's number. So if I have this, let's set it up first. So 1.5 moles of H2SO4 times in line. What do I put on the bottom? Moles. Whatever you're given goes on the bottom. And then what's my answer I want in? Molecules. So molecules or atoms gets 6.02 times 10 to the 23rd. Moles always gets the 1. Because this is the number of molecules in 1 mole, or up there, the number of grams in 1 mole. So now I want you to put this in your calculator. What'd you get? So I got 9.03 and then this little 23. Everybody get that? Okay, that means, and you may have gotten 9.03E23, like on your graphing calculator. Did you get that? Okay, so that, the E or the nothing, tells you times 10 to the. So this is 9.03 times 10 to the 23rd. So either way you see it, the top one is with these older calculators, the regular calculators. The bottom one is what a graphing calculator answer will show you. So 9.03 times 10 to the 23rd, I've got to round that. What do I got to round it to? How many significant figures in 1.5? 2. So now you come over the first two significant figures in my number. Remember, I'm going to keep the exponents, but it's the number out front I have to round. So 9.03 is 3 significant figures. So what would my answer be? 9.0 times 10 to the 23rd. I keep the 9.0. That's 2 significant figures. That 0 is now significant because it's after a decimal place. So you have some of these to practice. In chapter 3 at the end, we will do, and there. All right, so in this one, you ended up with 1.806 times 10 to the 24th. Did everybody put that in their calculator? Is that what you got? So how you're going to put this in, remember, and you can write yourself like the note with this one. So just take 3 times 6.02 EE 23. Okay? So just write it under here. To do the math, it would be 3 times 6.02. Then you push the EE button and then the 23, not 24, and then equals. So that's kind of like the steps to solve. Can I keep that number? How many significant figures do I need? Only 1, right? Because I have 1 significant figure here. So that means the 1, the next number is an 8. So what does that change it to? 2. So it'd be 2 times 10 to the 24th. I still keep times 10 to the 24th. So that doesn't get changed or rounded, just the numbers out front. So here's the one that's the real challenge. So this one, you want to go from molecules to moles. So in this, again, you don't have to figure out formula mass. You're just going to use Avogadro's number, but do make sure that you write it out. So 1.3 times 10 to the 21st molecules times in a line. What goes on the bottom? Molecules. Moles goes on top. So it's 6.02 times 10 to the 23rd on the bottom. So this one's the real challenge to see if you can put in the double exponents for this. So I got 0.00215946 moles. Everybody get that? That's a 2. 0.00215946. Anybody not get that? Okay. Okay, so I put in 1.3 EE 21. Then I did divided by 6.02 EE 23. What did you not do? Oh. Yeah, that'll add a problem. Okay? So see, did you get that? Make sure you can put it in your calculator. That's really the reason why people get these ones wrong. It's because they don't know how to put the exponents in the calculator consistently. But remember that EE, that's actually times 10 to the, so it's actually putting your number in that exponent value. And the nice thing about the EE is it puts brackets around those exponents. So if you remember doing math, like with other calculators, you'd have to put those parentheses around anything with an exponent. If you use the EE, you don't. It automatically puts those parentheses in there for you. So that's one of the reasons why I kind of like it, is I think it makes it a little simpler.
And you use this formula when it says moles.
If you have molecules to moles or moles to molecules, then you're going to use Avogadro's number, right? So I kind of put it up at the top, that purple up at the top. If there's grams to moles or moles to grams, then I use the formula mass. But if molecules is one of the values in it, then I'm going to use Avogadro's number. Okay, so last question. I can't keep all these numbers, so what do I have to do? How many significant figures? 2, because see the 1.3 times 10 to the 21st, the 1.3, that's the 2 significant figures. So remember, you keep the zeros out front, but they're not significant. The first 2 significant figures I get to are the 2 and the 1. The next number's a 5, so what does that do? It's going to round it up. So this would be 1.0022. I keep those zeros out front because it shows the size of the number. But 0.0022, 2 significant figures in that answer. Okay, so again, like remember, I save these. So this will be posted tonight. It'll be posted along with all the other chapter 3 slides. So it's posted or listed as, if you look at the top, it's the chapter 3 marked up PowerPoint. So it's posted in exam 2 module in Moodle. So if you want to ever go back and look at anything, like versus like watching the lecture video, if you want to do that, you could check these ones. So if you're like practice them yourself, you could always check your answers. Like if you look at the blank ones, because the blank pages have the question, but not the answer. So the marked up ones always have the answer that's there.